In this section, we're going to connect the idea of orthogonal subspaces to the range and null space of a particular matrix that we usually call A. So to start off, recall that you can take a matrix A that's n by n and multiply it by a column vector, and this column vector has to be n by 1, and when you multiply it by this column vector, you end up with a column vector that's m by 1, where the m comes from here and the 1 is from here. I want to write down the definitions of the null space of this matrix A, the range of the matrix. I also want to talk about the null space of the transpose of the matrix and the range of the transpose of the matrix. And then we're going to talk about the orthogonal complements to all of these subspaces. So to start off, let's write the definition of the null space of this matrix A. So this is going to be the set of all x in Rn such that A times x is equal to 0. So we're sending all of the column vectors, and it's the set of all column vectors that are sent to the 0 column vector in Rm. So this 0 column vector, remember, is going to be an m by 1 matrix. So maybe we should write that as well. This vector is m by 1. Now you can prove this. The null space is a subspace of Rn. Okay, let's write down the definition of the range of a matrix. Now the range of the matrix is all of the vectors y in Rm such that A times x is equal to y for x in Rn. So what this means is you're looking at everything you get from y, for y. So if x is some vector, you can choose every vector in Rn and hit it with A, and it's going to give you a matrix y. Each time you hit it with A, you're going to get a different matrix y, or they might be the same matrix. But we're just seeing everything we get when we multiply by this matrix A. So that's called the range. And notice that this is going to be, again, you can prove this. This is a subspace of Rm, because this is the set of vectors that are m by 1. Let's talk about the orthogonal complements to these spaces. So to start off, what is the orthogonal complement to the null space? Well, this is just the set of vectors. Let's call it z in Rn such that z with x is equal to 0 for all x in the null space. So remember, in order to take an inner product, the vectors have to be from the same space. And the null space is a subspace of Rn, so the vectors we're looking at are also in Rn. And we want, in order for this to be the orthogonal complement, we want the vector z and x, when we take the inner product, to equal 0. Now the orthogonal complement of the range is very similar. In fact, I can just copy this and stick that right here. And the only difference I have to make is I can say it's the set of all z's in Rm, because this is a subspace of Rm, such that z with x is equal to 0 for all x in the range. Okay? Great. Now let's talk about the null space of the transpose of A and the range of the transpose of A. So what we're doing now, in fact, let me move this down. I'm going to remind you, we said that, let's put this in red. We said that A is n by n, and if we multiply it by n by 1 matrix, we get y m by 1. But if we take the transpose, this is going to be an n by m matrix, and we're going to have to multiply it by a column vector that's m by 1, since these will have to be the same. And what we're going to end up with is a column vector that's n by 1. I'm only putting hats on these because they're not the same as this x and this y. So the null space is going to be the exact same thing as this. So let's copy this. But there's going to be just a couple of changes. Well, what's going to be different? It's going to be the set of all vectors in Rm such that when you take the transpose of A and multiply it by x, you get the zero vector, but the zero vector has to be n by 1. And then the range of the transpose of the matrix is going to be almost identical to the range of the original matrix, so let's copy that. Put that here. Oop. Sorry about that. Put it here. Okay, but what's the difference? Well, the range is going to be a subspace of Rn, so we need to put this as Rn. We need to put a transpose here because we're dealing with the transpose of a matrix, and all the vectors x are going to be from Rm. Okay? And so this null space is a subspace of Rm, and the range of A transpose is a subspace of Rn. And of course we can talk about the orthogonal complement. So the orthogonal complement of the null space of the transpose of the matrix, well, we can copy this. In fact, we could copy both of these. Let me do this. I'm going to put it right here. Okay, oops. Like that. So the orthogonal complement of the transpose, the null space of the transpose of the matrix, is going to be all z in Rm, because we need to be the same size as the vectors in the null space. So we're going to put Rm such that when we take the inner product of z with x, we get 0 for all x in the transpose of the null space. The transpose of the matrix, that's that null space. And then the orthogonal complement of the range of the transpose of the matrix. So let's fix this. We're going to fix that and this right here. This is going to be a subspace of Rn, such that for all z in Rn, when we take the inner product with x in the range of the transpose of the matrix, we get 0. Okay, great. So we wrote all the definitions down. One more thing I want to remind you about, I'm going to put that at the top here. Let's put it in red. Remember that if we have a subspace S and its orthogonal complement, then S, and S is a subspace, let's say of Rn, then S plus its orthogonal complement is all of Rn. We could say that with the null space and its complement. So here we have that the null space is a subspace of Rn, and its complement, its orthogonal complement, is also a subspace of Rn. So the null space and the sum of the null space and its orthogonal complement, remember this is a direct sum, this is going to be all of Rn. And then the range, if you take the range and its orthogonal complement, they're going to be subspaces of Rm. So the range of a matrix and its orthogonal complement is all of Rm. And you could do this for the transpose as well. You could say that the null space of the transpose, the direct sum of that with its orthogonal complement, is all of Rm, because they're subspaces of Rm. And then the range of the transpose, the direct sum of it with its orthogonal complement, is all of Rn. So these direct sums are really important, but there's actually something really interesting about a couple of them. We can actually substitute the range for the null space of a certain, for one of these, and we're going to see that in just a minute. So that's what I mean by this question. Are there any relationships between the null space and the range of a matrix and the null space and the range of the transpose of a matrix? So the answer is yes. And let's see one of them. Let's let Z belong to the range of a matrix, its complement. And let's see what we can do with that. So if that's true, then Z with Y is equal to 0 for all Y in the range of the matrix A. Okay, that's the definition of the orthogonal complement. Any vector in the orthogonal complement, if you take the inner product with a vector in the original space, which is the range, we get 0. But since Y is in the range, we have that Y is equal to A times X for some X in Rn. Remember, that was the definition of the range. If you have something in the range, this is a vector in Rm. So remember, you have Ax is equal to Y. This is n by n, this is n by 1, and this is n by 1. So Z is also in Rm. And the definition of the inner product has to be 0 in order for this to be in the orthogonal complement. So since this is true, and that's true if and only if Z with Ax is equal to 0. Okay, what can we do with that? Well, when I first started telling you about orthogonal complements, one thing I told you was it's reflexive. So this is the same thing as AXZ is equal to 0. And I also told you that if you have a matrix here that's n by n, you can move it over here, but by taking the transpose. And you can prove these. And you can also look back in the other, I think this was the very first video on this section. I showed you this. Again, you can just use properties. Remember, you're taking AX transpose Z is equal to 0, and then take the transpose. These are going to move around, and you're going to get the same thing. So what does that mean? So first, let's write this out. This is saying that X transpose times A transpose Z is equal to 0. And this is true for all Y in your range, okay? And if it's for all Y, there's some X in Rn. Now, X is any vector in Rn. If you take a vector in Rn, you apply A to it, you get some vector in Rm. So we can be very specific, because it's going to work for every single vector in Rn. We can be very specific. We can let, for example, X be 1, 0, 0. Or X, we could say X is 0, 1, 0, and so on. So why am I saying this? Well, this statement is true for all X, all column vectors X, when you take the transpose and multiply it by this new vector. Now, this vector is a vector in Rn, because this is in Rn, and this has to be in Rn. So ATZ, that's going to be some vector. Let's call it Z1 hat, Z2 hat, and so on to Zn hat. And the reason I'm doing that is because what I'm getting is this works for every single vector X. So how about 1, 0, 0, 0, Z1 hat, Z2 hat, Zn hat. This is going to be 0. So what does that tell you? If you do the dot product, you get that Z1 hat is 0. Since this works for any X, you could also do it for 0, 1, 0, all the way to 0, Z1 hat, Z2 hat, and so on. And this tells you, because this is equal to 0, this tells you Z2 hat is 0. And you continue this process, you're going to see that this has to be the 0 vector, because Z1 hat is going to equal Z2 hat, which is going to equal Zn hat, which is 0. So what we're saying is that A transpose Z has to equal 0. So let me erase this and write what I'm trying to get at. So what I'm saying is, this implies ATZ is equal to 0. Now, remember that Z is a vector in the range, the orthogonal complement of the range. Let's go way back up here, see? But at the same time, I'm saying that when I multiply it by the transpose, I get 0. So then Z belongs to the null space of the transpose of the matrix. And these are if and only if statements. So what happens is the range, the orthogonal complement of the range, is actually the null space of the transpose of the matrix. This is really important, and this is something I would want you to memorize. So what does that tell us? We know that the null space plus its orthogonal complement, let's do the range. The range plus its orthogonal complement is all of Rm. But from that you can see that the range plus the null space of the transpose is all of Rm. Okay. Something else we can do is we can substitute a transpose in this, and we get that the range of a transpose perp is equal to the null space of A, because the transpose of the transpose is A. And that tells us, let me circle this one, that the null space, we know that if we add its orthogonal complement, we get Rm. So now we know that the range of the transpose, let me erase this. I'm just going to plug in A transpose here and A here, so I get the range of A transpose plus the null space of A, that is Rn.